this video is a quick introduction about how the blockchain works. A blockchain basically consists of individual blocks which contain your data and a particular hash. If we look at the individual block, an individual block will contain the previous hash if there is a previous block behind this, and a nonce value, which could be a very long number, and the data. The data could be arbitrary. You can store any arbitrary data in a particular block. Then a timestamp when this block was generated, and a hash. The previous hash is basically pointing to the hash of the previous node. The value of nonce is used in controlling the difficulty of validating this entire blockchain whenever a new block is attached to the existing blockchain, which is also called mining. So the data field would be any arbitrary data. You can feed any arbitrary data you want in the data field. Then the hash is generated as a SHA of the data from the previous hash, the nonce value, the data, and the timestamp. Once that data is generated, whenever we want to add another node in our blockchain, we continue this process. We take the previous hash into the structure in our data structure. Then we have the value of nonce, which we could vary to satisfy the difficulty requirement of our mining. And then again, we have the data, which we can, whatever data we want, we can feed in the data field, the timestamp, and then there's a generated hash. Let's say whenever this node is added to the blockchain, we continue to adjust the value of the nonce such that we are able to satisfy the requirement of mining of our blockchain. Let's say we come up with a requirement that every hash on the node should start with 2 zeros. Then we continue to adjust one by one the value of nonce such that we are able to generate a hash which is always starting with 2 zeros. Again, we are adding a new node in the blockchain. We are taking the previous hash in our data structure. We have field for the nonce, and we have the data field. We have timestamp and the hash, which is computed from all the input data. The very nature of the blockchain, where the nodes are basically dependent on the hash of the previous node, it makes the data in the node in a certain way immutable to change. Let's say if one has to change the data in a particular node, then the hash of that particular node will basically change, and then one has to recompute all the nodes subsequent to that particular node in a blockchain, which will take enormous amount of computing power. The another property about these blockchain is they are operated in a distributed manner, which means all the nodes which are participating for this blockchain, they contain a replica of the entire blockchain. So whenever a new node is added, there is a consensus among all the participating node if they have also arrived at a same hash before a node is actually attached permanently to the blockchain. Even if one of the actor is able to counterfeit the data on one ledger and then recompute all subsequent nodes correctly, because of the very nature of distributed consensus, it will not be able to permanently attach a counterfeit data in a distributed blockchain. So how does Ethereum leverages this blockchain technology? So using Ethereum, you can write out decentralized contracts. What basically these decentralized contracts are, these are decentralized business logic, which are not controlled by any central entity. How cool is that? So how does that work is you write out these contracts, these small snippets of business logic in a programming language called Solidity, which is then compiled to a bytecode and then inserted into the blockchain in this data field. Since we saw that these blockchains have a inherent trait of being immutable and also decentralized, so these contracts or these snippets of business logic, they become decentralized. Now using these centralized application, you can essentially write out applications for industries which are inherently very non-trusted. For example, donations or lottery, because now no one entity is able to control the business logic, which would, for example, pick up the winner for a lottery or pick up the recipients of the donations. Now we will see an example where I have written out a contract for a donation campaign, where basically we can start a donation campaign, a donation contract, and The donation contract basically requires a minimum amount of approvers before the money can be let out. Then you can contribute to this donation contract by calling a contribute function on this contract, and it has a certain validation in place where it requires a minimum value of 0.01 ether. Next, what we do is we add the sender, whoever is the sender of that particular ether, as one of the approvers who are eligible for this donation campaign. So whenever we need to take out money from this donation campaign, so we will also check if the approver has actually validated that request. So for tracking that request, we are saving that approver in a mapping field, called approvers. Then we increment our approvers count, which is basically used for checking or validating on the minimum amount of approvers required for finalizing a request. So then we have a create request function where the manager or the person who has created this contract is able to create a request for sending out the money to some particular address. So the way the validation works is we have created a restricted decorator. So this is how the functions are. So this is how the function decorators are created in Solidity. So we specify modifier. We specify a modifier and the name of the function decorator. What I'm doing here is I'm looking at the message.sender and comparing that to the manager. The manager is the person who has created the campaign or the contract. So this is how I'm restricting certain function calls which can only be executed by the managers. So next we create a request object with the requirements of withdrawal of the money. So there is a description, there's a value, the amount of Ethereum that we want to take out from this particular contract, and the recipient where we want to transfer this money, and a Boolean flag basically to track if the request is completed or if it is not completed, and the amount of approval that we have received for this particular request. Then we store this request in our blockchain. If we look at our request field, this is a storage field where we are storing, this is a storage field for the request objects where we are storing all the request objects. Now, when it comes to approving the request, what we do is we take out that particular request and we use the storage modifier here to specify that we are looking at a field value which is actually referencing the block storage. So all these fields that you see, these are the block storage variables, which means that these are actually stored in the actual data block. These are actually stored on the actual data block, and these are not in-memory variables. So we are referring to that request with this storage modifier. Now we look at the approvers, we check that the person who is giving an approval, he has to be part of the approvers. And the way we add those approvers is whenever the person contributes, we add the person as the approver we store that person as an approver. Next, what we do is we look at the request and we look at the approvals and we see if the person has already approved. If the person has already approved, we cancel the request there. Next, what we do is we mark the sender as one of the approvers for the request and we store that in the request. Next, we increment the approval count for that request. Finally, when it is time to take out the money, we call the finalize request, which is again restricted. So only the campaign creator can call out the restricted functions. We look at the request from the block storage and then we check if the minimum approval count requirement is fulfilled for that particular request. And then we check if the request is already completed. If it is not completed, we throw an error. Otherwise, we transfer the Ethereums to the destination which is requested by that particular request, and we mark the request as completed. Now let's see how this is all compiled. So this was written in Solidity programming language. To compile this Solidity code, we have a compile.js where we are using the Solidity compiler. We are requiring the Solidity compiler. We are taking the file path for that donation campaign Solidity file. Then we are using the solidity.compile to compile the Solidity contract. So solidity.compile will spit out the bytecode and the definition for the contracts for all the contracts that you specify. So we have to just pick up the output which is specific to the donation campaign. So this is how we are going to pick up the bytecode and the interface which is required for the donation campaign from the output of the Solidity compile. So when it comes to deploying this contract to a real network, we will use a HD wallet provider from the truffle library, and then we will need a web3 library. And this is the output from our compile source code. We get the interface in bytecode, which is available under the contracts colon donation campaign. So interface provides a definition for the JavaScript to know how to communicate with the bytecode or the contract, and bytecode is the actual bytecode definition of our contract. So first we need to initialize our provider. So I'm here creating an instance of the HD wallet provider, and I'm providing the 12-word mnemonic, which will actually result in all the accounts which I have created on my MetaMask on the test network. And second is the endpoint of my test network. So I'm here using Infura for generating this endpoint, which I'm using for communicating with the Sepolia test network. Then I'm creating an instance of Web3 and I'm passing in the provider. So once that is done, it is very easy to deploy your contract on a test network or a real network. Make sure that you're not running this with a real wallet because it consumes money to deploy. First and foremost, what we do is we get all the accounts. We get all the Ethereum accounts associated with our wallet. Then we attempt to deploy from the first account in our wallet. And we create an instance of eth.contract. We pass the definition of the contract. Then we call the deploy command and pass in the data, which is the bytecode. We also need to pass in arguments. Since our contract, if we look at our contract, one of the requirements of the constructor function was the minimum amount of approvals required. So since that is required, I need to pass in the argument. So I'm just specifying 0 minimum requirement for the approvers. So therefore I'm passing in a 0 value here. And then I'm passing a generous amount of gas, which can be consumed for deploying this contract on the network. Then I'm specifying from which account this needs to be deployed. Then for debugging purpose, I'm doing a console out of the interface definition. And once that is deployed, I will also get the address of that contract on the blockchain. So next is how do we get this 12-word mnemonic or the test account? So for that, I have installed MetaMask. So once you install MetaMask, you need to enable show test networks. And from here on, you can select one of the test networks. I'm using Sepolia here. And to seed my account, I have used Alchemy service here to receive 0.5 Sepolia ETH in my account. Once you have your account funded, the next thing you need to do is you go to your settings and go to your security and privacy. And then you're using this reveal secret recovery passphrase. Now from this, you can copy the passphrase, which will include all the account related information for all the accounts that you have on the MetaMask instance. Second, I'm using the service from infura.io to interact with the Sepolia Ethereum blockchain. Once you have the deployment address from the console, you can use something like Etherscan, which actually tracks and monitors a couple of blockchains, a couple of Ethereum blockchains. So the way to do that is you can come to sepolia.etherscan.io. You can search for the address of your blockchain. So if I look at it, if I look at the transactions associated with my MetaMask account, I can see that I have received a 0.5 ETH as a transaction. And then from that account, I have done a contract creation, and that has been sent out to this particular address, which is the deployment address. Again, using a very similar approach, you can search for the deployment address of your contract, and you can list out all the transactions which are happening on your contract. So this approach of deploying can be used in a backend service because you can keep the 12 phrase private to yourself, but you cannot attempt to do something similar on a front end. So if you want to do something similar on the front end, what needs to be done is you need to have this MetaMask installed by your customer or the consumer of your application. What MetaMask will do is it will inject an instance of Web3 object, which is connected with the MetaMask account in all the pages. Again, if you only want to pick the provider from the Web3 instance, you have to do web3.current provider, which will provide you the initialized provider which will provide you the correct provider for interacting with the accounts listed in MetaMask, which you can actually replace in your constructor call to Web3 library. So once Web3 is initialized, you can use the rest of the code as it is. You can use the rest of the code to deploy contracts, or you can use the rest of the code to call functions on an already deployed contract. One thing I want to show, and one additional thing I want to show, is how we can test out our Solidity contract locally. So what we are using here is a Ganesh library, and what this will basically provide is it will provide a locally running Ethereum network for you to test out with all the accounts preloaded and preset. Then we require our Web3 library. Then we require our assert library to do assertions. And next we initialize our Web3 with the Ganesh provider, which will point out to a local network. And again, from the compile, we include our interface and the bytecode. First and foremost, what we do is before every test that is run, we get all the accounts listed with our provider. Here it will provide the accounts, test accounts from the Ganesh library. And then we have a minimum approval count, which is required as an argument to our contract. So first and foremost, we define the contract and we deploy the contract on our test network from the initial account we have associated in the local Ethereum network. So for the first test, what we do is we deploy the contract and we assert that we don't have an undefined address. So that's the first definition. That's the first assertion and the first test we do. Next, we verify that the person who has created the contract is indeed the account which has actually created that contract. So what we have here is a manager field, which we are setting whenever the contract is created. So since this field is public, and in Solidity, if a field is public, it is available for access from the external world. So here what I'm doing is I'm calling this method manager to retrieve the value of the manager, and then I'm asserting that the account 0 is indeed the person or the address who has created this contract. Next, what I'm doing is I'm trying to contribute to this contract. I'm sending 0.02 Ether to this particular contract from the account number 1. And then we will look at the contribution code. We can see that the minimum requirement is satisfied. And then we add the sender as one of the approvers for this campaign, and we increment the approvers count. Then we look at the approvers value, since again, this mapping is actually public. So we retrieve the value of the approvers and we check if that account 1, the address associated with the account 1, is indeed a contributor. In the next test case, we again call the contribute function with a value of 10V. And as we can see in our requirements that we have a minimum of 0.1 Ether that needs to be sent out. So this requirement will basically fail, and we assert that this is throwing an error. So that is why we are asserting an error. Next, we have a test case to verify that we are able to create a request from the creator account. So we call the create request function, which can only be called from the account which has created the contract. So what we are creating is a request object for description of buying the batteries. And then we are requesting an amount of 0.01 Ether, which needs to be sent out to the account number 1. And for executing this function, I'm sending it from the account 0 so that the restrictions would not apply. So we are able to satisfy the restriction function. And then I'm passing a generous amount of 1 million. Once the create request is resolved, then I'm looking at the request to see if we have the request added in our, then I'm looking at my request array to see if my request is actually created and stored in the request array. Finally, I have a test case here which goes through the entire process end to end. I'm contributing 0.02 Ether from the creator account to this campaign. Then I'm creating a request of taking out 0.01 Ethereum and sending it out to the account associated with the first index. Second, then I'm creating an approval request from the creator account. If we look at the approved request, we can see that the sender has to be, if we look at the approved request, we can see that the sender has to be one of the contributors. So only if the sender is one of the contributors, we allow the approved request and we mark it as approved. And then we look at the final attempt to finalize the request and send out the money. We validate that the request has fulfilled the minimum approval requirement. In this case, it will be 0 because we have deployed the contract with a minimum approval requirement of 0. So So we will send the final. So this should also pass. And what I'm doing next is I'm validating. I'm getting the balance for the account associated with the first index, and then I'm converting that to, so these balances are actually stored in vunit, and then I'm converting that to ether. And after that, I'm asserting that the value has crossed a certain threshold. So if I run this, I should see all the tests passing. Cool. You can also use the Remix IDE from the Ethereum to test out your contracts and also deploy the contracts on a real network. So I have the same contract written here, copy pasted in the Remix IDE. And here you will find all the options to deploy and run that contract. You need to ensure the correct environment that you're deploying this to. So this Remix VM is actually a test network which you can use for testing out your contract. And once you need to deploy it to a real network, you can use the MetaMask provided here. And then you can use the deploy button to deploy out your contract. So this is using the actual Sepolia test network to deploy. So I'm going to confirm it. So next, let's see what will happen is, so this will take some time, like 15-30 seconds for this to be available on the actual Sepolia network. And once the deployment is done, you should see your actual deployed contract here. So now the deployment is actually done. We can see that our contract is now available. We can call all the functions which are provided by this contract. And we can also see on Etherscan our newly created contract on the blockchain. That's all for this video. Let me know if you have any questions in the comments below.